Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. Tonight, we are going to explore many different chemical elements, their properties, their abundance or rarity, and their relevance in everyday life. Some are very famous, and others are little known, but they are all interesting to discover. I will also tell you about the periodic table of elements, which we are going to follow and detail in our systematic exploration. And I will explain plenty of other things about what distinguishes elements, their atomic structure, how and why they combine to form molecules and chemical compounds. We will see where they are found and how they are used in industry or research. So we have a lot to discuss, so much that this story is going to be in 3 parts. Tonight we will cover elements 1 to 12, from hydrogen to magnesium, and we will continue our review in the next episode. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. You will gain access to 25 exclusive episodes. We add a new one every month, and you can listen and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon, as well as links to different streaming options, which may be better suited for you. You will find them in the description of the episode. And now, before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries. Assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath. And when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, off we go. So let's get started with the first element, hydrogen. Hydrogen is thought to be the most abundant chemical substance in the universe. It certainly is in our galaxy. It is estimated that roughly 75% of all matter in the universe is hydrogen. And this element could be called the simplest of all of them because it is the lightest. And its structure is simpler than others. What does this mean to understand what a chemical element is? To answer that, we need to talk about the structure of atoms and what makes one element distinct from all the others. As you know, all atoms have a nucleus, a central region made of at least one proton, a small subatomic particle. Another type of particle, very similar to the proton, and also found in the nucleus, is the neutron. And to this nucleus are bound one or several electrons that change place very fast and form a sort of swarm around this nucleus. This is what an atom is like, and what defines an element in the periodic table is the number of protons in its nucleus. The number of protons is called the atomic number. Hydrogen has 1 proton, so its atomic number is 1. If you had 2, which happens when 2 atoms of hydrogen merge, when they fuse, it would no longer be hydrogen, it would become helium, the element with atomic number 2. As you also know, atoms are not the smallest possible units of matter we know of. They are made of smaller particles. We just talked about protons, neutrons, and electrons, and these particles are themselves made of even smaller bricks, smaller units. Atoms can gain or lose particles. They can be broken sometimes, or forced to merge, even though it takes a lot of energy to do that. So they are far from being a primary unit of matter. They are made of different, smaller bricks. So what makes the atomic level so relevant in this case? Why do we focus so much on atoms when we talk about matter? First, because atoms happen to be a very common and stable form of organization of matter. Not all matter in the universe is organized into atoms. There are also free particles. But most of the matter we know of is structured into atoms. Another thing that makes atoms very relevant is that each chemical element corresponds to a particular type of atom. When subatomic particles are not structured into atoms, there are no chemical elements. All the elements we know of, from hydrogen to the heaviest elements, have certain properties that distinguish them because their atoms are structured differently. Hydrogen, gold, iron, uranium are made of the same basic particles. They are distinguished from one another and have different properties, including their appearance, their mass, and their ability to react with other elements, because their atoms are different. This is, in fact, how an atom is defined. Atoms are the basic units of chemical elements. We will see a lot more about atoms and how they interact. But to continue with hydrogen, why is it the most abundant element in the universe? It is believed that the first combinations of particles into atoms after the birth of the universe, following the Big Bang, created primarily hydrogen atoms. The formation of protons, which form the nuclei of hydrogen atoms, occurred almost immediately. It is believed within the first second after the Big Bang. But it took much longer for these protons to become associated with or bound to an electron, making them electrically neutral. Both particles, protons, and electrons, are electrically charged with opposing signs. So when an atom has the same number of protons and electrons, it has no net positive or negative charge and is electrically neutral. But at the start, just after the Big Bang, matter was believed to be too hot for electrons to remain bound to protons. First, it had to cool down, and only after it had cooled sufficiently, at a time estimated to be about 370,000 years after the Big Bang, could electrons and protons begin to bind together and remain bound. So the first atoms would not have appeared with the universe itself, but rather a few 100,000 years later, when the original heat, the extreme concentration of energy, had receded enough for atoms to form and remain stable. At first, all atoms would have been relatively light: hydrogen with 1 proton, helium with 2, and lithium with 3. All the other heavier atoms or elements with more protons, more particles in their nuclei, would have appeared later and be the product of subsequent fusions between these smaller atoms, especially hydrogen. We will also elaborate on this later, and I will tell you how other elements would have formed. But why is hydrogen called that? Hydrogen comes from Greek and means water former or water creator. The name appeared after it was discovered in the 18th century that this gas, because under standard conditions on Earth, pure hydrogen is a gas, could burn or explode and produce water when it came in contact with air, or more precisely, with the oxygen in the air. When something burns or explodes, it is in fact a chemical reaction, and that is what is happening here: a chemical reaction in which hydrogen and oxygen recombine into a molecule called H2O, 2 atoms of hydrogen and 1 of oxygen, better known as water. Hydrogen got its name from its capacity to produce water when it reacts with oxygen. There is much more that could be said about hydrogen, but let's move to a second element, the element with atomic number 2. With 2 protons in its nucleus, helium. Helium is not very present in our daily lives, unlike hydrogen, which is a major component of our bodies. But don't underestimate helium, because at the scale of the universe, it is a big deal. About 24% of the total elemental mass in the universe is helium. I told you before that hydrogen was by far the most abundant element, accounting for close to 75% of all elemental matter. So with these 2 elements, we already have close to 99% of the elemental mass in the universe. The bulk of matter consists of hydrogen and helium. Helium is very present in stars. It is the product of nuclear fusion in stars. You know that the fuel of stars during most of their lives is hydrogen. Inside the stars, in the extreme conditions of temperature and pressure, nuclei of hydrogen atoms are forced to merge, and when they merge, this fusion liberates a lot of energy. This is what stars live on, and the product of this fusion is a new helium atom, an atom with 2 protons in its nucleus. So there is a lot of helium inside stars, and the more a star ages, the more helium it accumulates. Apart from stars, helium is also a big component of gas planets like Jupiter or Saturn. On rocky planets like Earth, Mars, or Venus, it is present only in small quantities under normal conditions of temperature and pressure. Under standard conditions, it is a light, colorless, odorless, non-toxic gas, and one well-known use of its low density is as a lifting gas in balloons and airships. Other than that, helium is used in various industrial processes at very low temperatures, low enough for it to be in liquid form. It is used in cryogenics, the science of very low temperatures, close to absolute zero. It also serves to cool electromagnets, to pressurize environments, and to manufacture silicon wafers. In electronics, wafers are thin slices of semiconductor material. A wafer serves as the substrate on and within which microelectronic devices are built. The largest reserves of helium on Earth have been found in natural gas fields, especially in the United States, which is the largest supplier of this gas today. One thing helium is famous for is that it is classified as a noble gas, together with other gases that are grouped with it in the periodic table: neon, argon, krypton, xenon, and radon. As we advance, I will tell you about the logic of the periodic table, because it is much more than a list of elements. It also tells us about their properties and groups related elements together. Noble gases are one of these groups. There are 18 groups in total, and the elements within each group share similar properties. For example, all noble gases are odorless and colorless, and they all become liquids at very low temperatures. They are called inert because they have very low chemical reactivity. They typically do not react with other elements. Why don't they? This is because of the configuration of their electrons, the number of electrons in an atom, and the way the swarm of electrons around the nucleus is arranged are major factors that determine reactions between elements. When elements react with one another, which means that new molecules or compounds are formed, or existing ones are broken apart and replaced by others, atoms share electrons, or gain and lose them. For reasons that have to do with the conservation of energy, atoms tend to saturate their outer electron shell. Typically, the first layer of electrons around an atom has 2 slots for electrons. When there is only one electron in this shell, as in hydrogen atoms, which typically have 1 proton and 1 electron, the atom will be prone to associate with another atom that is also missing 1 electron in its outer shell. This is why a very common form of hydrogen is not isolated hydrogen atoms, but rather dihydrogen, a molecule made of 2 hydrogen atoms. The 2 atoms are their electrons, which gives the dihydrogen molecule 2 electrons in its single electron shell, making it a relatively stable association. Now, the first electron shell has 2 slots, and helium atoms happen to have 2 protons and 2 electrons. So the atom does not need to associate with one or several others to complete its electron count. This is the reason why helium is inert. It does not need, nor does it seek, to react with other elements, because in that respect it is self-sufficient. Now, the first electron shell has 2 slots, but the following shells have more. They have 8. And this is why there are other elements in a situation similar to that of helium. The next one is neon, which has an atomic number of 10. 10 because it has 10 protons and also 10 electrons, making it electrically neutral. This means its first electron shell of 2 electrons and its second shell of 8 are both full. This is the reason why neon shares many properties with helium, in particular, same lack of tendency to undergo chemical reactions, the same inertness, and the following noble gases in the periodic table. The other members of the same group, argon, krypton, and xenon, have the same characteristic. Their outermost electron shell is full. They are not inclined to react except under extreme conditions that do not occur in our everyday environment on Earth. And this is why these gases are used in applications where no chemical reaction is desired. For example, they can be used to create an atmosphere around very reactive materials to prevent explosions or unwanted reactions. To mention just one well-known practical use of helium, a noble gas that is not prone to reacting, I could point to the replacement of hydrogen by helium in Zeppelins after the Hindenburg disaster. The accidental destruction of the Hindenburg, a German Zeppelin, failed with hydrogen as it was landing in New Jersey after crossing the Atlantic in 1937. Hydrogen was cheap and efficient as a lifting gas for balloons and Zeppelins, but it is also highly flammable, and it was only a matter of time before an accident occurred. Helium is much safer by comparison. It cannot burn or explode. Replacing hydrogen with helium did not save Zeppelins, which still disappeared because they were too slow and not very cost-effective compared with airplanes. But if Zeppelins ever return, it will probably be with a non-reactive gas, like helium. Now let's move on to element number 3, our first metal, lithium. Lithium has been under the spotlight in recent years because it has become a strategic resource with the rise in demand for rechargeable batteries, a crucial component of electric cars in particular. There are several technologies for these batteries, but those using lithium are currently the most effective. Lithium is highly reactive, and it is always found either combined with other elements in compounds or dissolved in ocean water. But why is it so reactive? For the same reasons helium is not reactive. Basically, it is because of the electrons. Lithium has 3 protons, so it tends to bind 3 electrons with opposite electric charges. But we saw earlier, when I told you about helium and the noble gases, that the outer layer of electrons was important for chemical reactions. Lithium has a first electron shell with 2 electrons, which is full, and on top of that, 1 lone electron in the next shell, which could hold up to 8. So this third electron is in an awkward position. It can be lost, which turns the lithium atom into an ion, an electrically charged atom, because it lacks an electron. These lithium ions have high solubility. They mix easily with water, and this is why lithium can be found in seawater, although in concentrations too low to be economically mined. It is found mainly in salt pans or salt flats, which are places where a pool of salt water has evaporated, typically in deserts. The minerals found in these expanses of salt are much more concentrated than in ocean water, and from them, lithium and other minerals can be extracted. This is why the largest exploitable lithium deposits are found in countries with extensive salt flats, such as Chile, Argentina, Bolivia, and Australia. A general rule when it comes to the abundance of elements in the universe is that the simpler and lighter the atoms are, the more abundant they tend to be. We have seen before that hydrogen and helium account for most of the atomic mass in the universe. But even though lithium is also a relatively light and simple element with its 3 protons, it is not very abundant and is actually less common than some of the elements that follow in the periodic table. This sounds odd or paradoxical, but it is because the nucleus of lithium tends to be unstable. It does not take much for it to break apart, to undergo fission, and lose one of its protons, which transmutes it into helium. This is why it is an exception to the rule that lighter elements are more abundant. Lithium is relatively rare for such a simple element, and it is also the first member of a family of elements with similar properties, just as helium was for noble gases. This family is called the alkali metals, and it includes lithium, sodium, potassium, and larger, rarer elements such as rubidium, cesium, and francium. Alkali metals stand in contrast to the noble gases. In a sense, noble gases are inert, whereas alkali metals are highly reactive. And the reason for this property is that 1 extra electron, which makes them very prone to chemical reactions. So typically, alkali metals are not found in pure nature. They are associated in molecules with other atoms due to past reactions with them. And when refined, a block of alkali metal needs to be kept in an inert liquid or an inert atmosphere, because just a contact with the air could provoke a chemical reaction, a combustion. Our next element is beryllium, with atomic number 4. It is another element that is relatively rare. It appears mainly in the cores of stars as they approach the end of their lives and begin to fuse heavier elements because their hydrogen reserves are depleted. But this beryllium disappears quickly because it fuses into even heavier elements. On Earth, beryllium is a relatively minor component of the Earth's crust, but it can be found. For example, somewhat anecdotally, it is present in certain gemstones, such as aquamarines and emeralds. You now understand how electron shells work. So beryllium has a first complete shell of 2 electrons, and in its second shell, it has 2 electrons out of a possible 8. This makes beryllium and the other members of its family, which also have 2 electrons in their outermost shell, rather prone to chemical reactions. In fact, under natural conditions, beryllium is not found alone. It is always combined with other elements, forming different minerals. This family of elements, headed by beryllium, is called the alkaline earth metals, and it includes other elements we will review later, such as magnesium, calcium, strontium, and radium. Element number 5 is boron, another relatively rare element with a few industrial uses. One of the uses of boron is as a neutron capturing agent, particularly in the nuclear industry. But what does that mean? And how does it work? Until now, I have told you mainly about protons in the nuclei of atoms, protons that determine the nature of an element and its atomic number. But there is a second type of particle that can be found in the nuclei of atoms, neutrons. Neutrons are a lot like protons, but without an electric charge. And for a given element, the number of neutrons can vary. A different number of neutrons means that some properties will be slightly different, starting with mass. For the same number of atoms, there is more matter when there are more neutrons. So depending on the element, there can be several versions of the same element, each with a different number of neutrons. These variations are called isotopes. Typically, an element can have different isotopes, some of which are not very stable. They may have too few or too many neutrons, which causes them to decay or transform into another element. So many isotopes are unstable and short-lived. They do not last long. But many elements also have naturally occurring isotopes that are perfectly stable, or stable enough to last a very long time before eventually decaying. Boron, for example, has 2 naturally occurring isotopes, one with 5 neutrons and one with 6. The one with 5 neutrons is called boron 10 because it has 10 particles in its nucleus, 5 protons, which make it a boron, and 5 neutrons. The other isotope with 6 neutrons is called boron 11, 5 protons and 6 neutrons. In total, however, 13 isotopes of boron have been discovered, ranging from boron 7 with only 2 neutrons to boron 21 with 16 neutrons. Unlike boron 10 and boron 11, which are stable. All others vanish quickly. Those with a mass number below 10 tend to decay into helium, while those above 11 tend to decay into carbon, the next element I will tell you about. Boron is useful as a neutron absorber in nuclear facilities because it readily captures neutrons, and free neutrons are what sustain chain reactions of fission in a nuclear reactor or a nuclear explosion. Heavy atoms that are prone to fission capture these free neutrons. This makes them unstable. They split into lighter atoms and also release more neutrons, which become available for further reactions. This is the principle of nuclear chain reaction. Boron is useful as a means of control because it is neutron hungry. It tends to stop or poison, as is often said, the free circulation of neutrons that sustain the chain reaction. So it is useful for controlling a nuclear reactor or, in the event of an accident, for capturing neutrons and reducing the neutron flux, helping to stop further fission reactions. Now, let's move on to a very important element, without which organic life, as we know it, would be impossible. Carbon. Carbon has atomic number 6. It has 6 protons, and it is estimated to be the 4th most abundant element in the universe, after hydrogen, helium, and oxygen. In the Earth's crust, it is the 15th most abundant element. But in our bodies, it ranks second by mass after oxygen. Our bodies are made of about 18 to 19% carbon. What distinguishes carbon from other elements is the number of forms and compounds in which it can be found. First, because carbon atoms can bond together in very diverse ways. As you know, diamond is pure carbon, and it is the hardest natural material we know of. But graphite, which is used in pencils and is soft enough to be used for writing, is also pure carbon. The only difference between the two is how the carbon atoms are arranged. There are other forms as well. Carbon can be shaped naturally or artificially into nanotubes or different kinds of meshes. These different arrangements are called allotropes. All elements can exist in different states. They can be liquid, solid, or gas. Allotropes are something else. They are different arrangements of atoms. Atoms can be bonded together in different ways. So diamond and graphite are 2 allotropes of carbon. They are both made of carbon in the solid state, but their atoms are arranged differently. The different arrangement of carbon atoms gives them very different properties. Apart from its allotropes, another remarkable property of carbon is its unique ability to form chemical compounds under standard conditions. With its 6 electrons, 2 in the first shell and 4 in the second, it has the capacity to form up to 4 bonds with other atoms. This property, combined with its relative abundance, has led to the existence of a huge number of carbon compounds. More than 200 million have been described and indexed. There are relatively simple molecules and compounds such as carbon dioxide, one carbon atom and two oxygen atoms, carbon monoxide, and the many hydrocarbons, which, as their name suggests, are compounds of hydrogen and carbon. But this is just the tip of the iceberg. There are also countless polymers, very large and complex molecules in which carbon, oxygen, and hydrogen are abundant. All biological life forms we know of rely on carbon chemistry, and this is why even astrobiologists, people who study the possibility of life beyond Earth, how it could appear, spread, and evolve, generally believe that carbon would also be crucial to extraterrestrial life forms, not out of lack of imagination, but because of the chemical properties of carbon, its ability to bond with many other elements in many different ways, and to be used to build living structures as well as transport energy. Maybe a life form without carbon is possible, but it seems much more likely that life would include carbon. This comes down once again to the properties of this element, which are determined by its atomic structure. And on top of that, there is this abundance. As we said, it is the fourth most abundant element in the universe. After carbon, we have nitrogen, which is number 7. Nitrogen is another abundant element on Earth, and the proof is that you are currently immersed in it. Almost 80% of the air we breathe is nitrogen. So under standard conditions, nitrogen is a colorless, odorless gas. After oxygen, carbon, and hydrogen, nitrogen is the fourth most abundant element in our bodies. It makes up about 3% of our body mass. It is present in particular in amino acids, complex compounds that are incorporated into proteins. Nitrogen is also vital to plants. It is found in nitrates and ammonia. Nitrates are compounds that nitrogen forms with oxygen, and ammonia is a compound of nitrogen and hydrogen. Both are important fertilizers for plants. We are reaching number 8, oxygen, which, as you know, is another crucial ingredient of life. There is oxygen in the air, about 20% in our bodies, and also in the ground. It would be easy to think of oxygen only as a gas because we breathe it. In reality, oxygen also forms oxides with many other elements. So much so that about half of the Earth's crust consists of oxygen by mass. Pure oxygen under atmospheric conditions is a gas, and its atoms tend to bind in pairs to form dioxygen, O2. Oxygen can also form water when combined with hydrogen, as well as all sorts of oxides with iron and sulfur and carbon, and in particular with silicon in the Earth's crust. Obviously, we need oxygen to breathe. What we call breathing is ultimately a chemical reaction. Oxygen reacts with molecules derived from food. This produces energy that we use, and a main waste product, carbon dioxide, which we expel. To continually extract this energy from organic molecules, living beings need to breathe continuously or almost continuously. We need a constant supply of oxygen, and this is what our lungs provide to our bodies. I told you that when pure, oxygen comes in pairs of oxygen atoms, dioxygen, or O2. But oxygen also has another form in the atmosphere with 3 atoms, O3, which is also known as ozone. Ozone is an allotrope of oxygen. You remember what allotropes are: different forms taken by an element under the same conditions, resulting from different arrangements of atoms. In the form of ozone, oxygen also protects life on Earth because ozone has a strong capacity to absorb ultraviolet radiation. I have already told you a lot about oxygen in previous stories, so for now, let's move on to our next element. Number 9, fluorine. As with all the elements I have told you about until now, fluorine is the first member of its group, and the group it heads is called the halogens. Apart from fluorine, the halogens include chlorine, bromine, iodine, and other larger elements. These elements have 7 electrons in their outermost electron shell, 7 out of 8 possible slots, and this makes them highly reactive. They strongly tend to attract another electron, just as lithium, which we saw earlier, strongly tends to give up its 3rd electron. So fluorine tends to react with almost all other elements, except noble gases like helium or neon, which are inert under standard conditions. Fluorine is a highly toxic gas. It is toxic because of its reactivity. When it comes into contact with moisture or water, it reacts readily. The compound it forms with hydrogen is a powerful acid. It also reacts with the skin, producing burns that can even resemble frostbite if the fluorine is liquid. But don't worry too much about it. Only improper handling of chemicals is likely to expose you to fluorine gas because it cannot remain long in the atmosphere before reacting with something else. There is a good amount of fluorine on Earth. It ranks 13th among the elements in terms of abundance in the Earth's crust, but it is found in minerals in combination with other elements, such as fluorite with a T, which is a mineral composed mainly of calcium and fluorine. We are reaching element number 10, neon, and with it, we are completing a little cycle because, as you remember, neon is the 2nd noble gas, the one that comes after helium in the noble gas family. Its outermost electron shell is full, with 8 electrons. So like helium, neon is not inclined to react with other elements. Neon is a good example of how elements are not evenly distributed throughout the solar system or the galaxy. In fact, it is very common in the universe. It ranks 5th in abundance after hydrogen, helium, oxygen, and carbon. But on Earth, there is barely any of it. It is found only in trace amounts in the atmosphere. So how is it that there is so little on Earth? This is because neon is very volatile and forms no compounds that would bind it to solids, unlike nitrogen or oxygen. So it is believed that almost all the neon in the early solar system escaped from the protoplanets that formed near the Sun, warmed by this new star, including all the rocky planets from Mercury to Mars, Earth included. This neon drifted far towards the outer regions of the solar system, beyond Jupiter, where it is relatively common, whereas we only have traces of it on Earth. One use of neon is in lighting. You probably know about neon signs, which were popular in the 20th century as commercial displays. They are gradually disappearing and being replaced by LEDs that imitate their appearance. But neon signs used neon and electricity to produce light. Inside a neon tube or lamp, neon and other gases are confined at low pressure between two electrodes. When sufficient current is supplied between the electrodes, the gas produces a luminous glow, and this is how neon lamps and tubes work. Element number 11 is sodium, the second alkali metal after lithium, and another rather common element on Earth, the sixth most abundant. You may remember that lithium was very reactive because of its single electron in its outermost shell, and sodium has the same characteristic. It has a first shell with 2 electrons, which is full, a second shell with 8 electrons, which is also full, and a single electron in the third shell, which can easily be given away by the sodium atom. So sodium is not found in pure form, but combined with other elements, often in the form of salts. But what is a salt, by the way? There is the common meaning of salt as in table salt, the mineral that can be added to our food. This table salt is sodium chloride, a compound made of equal numbers of sodium and chlorine atoms. This type of compound is called an ionic compound and could easily be confused with a molecule, but it is not really one. A molecule is an association, a group of atoms that share electrons. These atoms are chemically bonded. An ionic compound is something else. It is held together by electrostatic forces. In other words, it is a compound of ions. Ions are atoms or molecules that have a difference between their number of protons and electrons, which makes them electrically charged, either positively or negatively. For example, in the case of sodium chloride, meaning table salt, we have sodium atoms with an 11th electron that can easily be given away, and the same number of chlorine atoms with 17 electrons. They are missing just 1 electron to complete their outer shell. So chlorine atoms will take 1 electron from sodium atoms, making the chlorine ions negatively charged, whereas the sodium atoms, having lost 1 electron, become positively charged. These two types of ions attract each other because of their opposite electric charges. As they come together, they create a well-organized structure, a crystalline structure in which all the ions replicate the same arrangement. It is orderly, and electrostatic forces, in this case also called ionic bonding, keep the structure together. So these are not molecules. In fact, an ionic compound can be made of atoms with opposite charges, or of molecules that carry opposite electric charges and adopt this structure. In chemistry, a salt is any chemical compound made of positively and negatively charged ions held together by their opposite charges. It has no net electrical charge because the positive and negative charges balance each other. So table salt is a salt in the chemical sense. But there are many other possible chemical salts. Let's advance to element 12, magnesium, the second alkaline earth metal after beryllium. I mentioned earlier that beryllium was rare in the universe and on Earth because it was quickly depleted after its formation in stars. Magnesium doesn't have the same problem. It is produced in large, aging stars when they have consumed a large part of their hydrogen reserves and start to fuse heavier nuclei. In such stars, the addition of 3 helium nuclei to 1 carbon nucleus gives a nucleus with 12 protons. 3 times 2 from helium nuclei and 6 from carbon, and we get a new magnesium nucleus. This happens near the end of the life cycle of large stars that end in a supernova, which expels all this new magnesium into the interstellar medium where it can be recycled into new star systems. So like all the heavier elements from beryllium with atomic number 4 to the heaviest elements on the periodic table, the magnesium atoms we have on Earth did not form at the start of the universe with the Big Bang. They formed later, probably in stars that died and whose material was recycled from the solar system. Magnesium is a metal, but the term metal is a bit like salt. Its definition may depend on the context. So what is a metal exactly? Here again, there is the everyday definition. What we call metal in any material that conducts electricity and heat, that shows a lustrous appearance when polished or broken, and that is generally relatively heavy compared to other materials. So we kind of know intuitively what is a metal and what is not in our daily lives. Most of the time, we expect to find metals in a solid state at room temperature. But we also know that there are exceptions to this. For example, mercury is a liquid, and sometimes we use metal objects like aluminum ladders that are surprisingly light. But aluminum is a metal. Physics and chemistry need more precise definitions. In physics, any metal is any substance, not necessarily an element. It can be a combination of elements, like an alloy, any material or substance that is capable of conducting electricity when there is no heat at all, at absolute zero. And this definition can give counterintuitive results. All familiar metals, iron, copper, gold, etc., remain metals under this definition. But in some conditions, with the right pressure, plenty of elements can become metallic. For example, hydrogen. Inside large gas planets like Jupiter or Saturn, it is believed that hydrogen in the deeper layers of these planets is pressurized enough to become metallic, meaning essentially that it can conduct electricity. Sodium is regarded as a metal, but it can lose its metallic properties if exposed to extreme pressures above 2 million times atmospheric pressure. In that case, it ceases to conduct electricity. But at even higher pressures, it is theorized that it should regain those properties and become a metal again. So based on this definition, metal or metallic is as much a state, a property of material under certain conditions, as it is a characteristic. This tends to blur the frontier between metals and nonmetals. And then there is yet another definition, which is the one used in astrophysics. The term metal in astrophysics is applied more broadly to refer to all elements in a star that are heavier than helium, that is to say, basically all elements except hydrogen and helium. The definition contradicts the common definition used in chemistry and physics. In astrophysics, elements like carbon, oxygen, or nitrogen become metals when they are not in chemistry. So as you understand, it depends on the definition. The one from astrophysics is probably too broad for other disciplines. It makes sense in astronomy because it is about the genesis of elements in stars. But whatever definition of metal we choose, magnesium falls into this category. It conducts electricity under standard conditions and also at absolute zero. Another aspect of magnesium is its importance to life. Alongside the elements that really form the main building materials of our bodies, oxygen, carbon, and hydrogen, magnesium is one of the many elements that are present in small quantities but are essential to life. It is found in every cell and in hundreds of enzymes. Enzymes are proteins that act as catalysts for chemical reactions in our bodies. We absolutely need them to ensure our metabolism works correctly, and these enzymes require magnesium ions to function. For plants, magnesium is necessary for the synthesis of chlorophyll, which is essential to photosynthesis. So here again, we have an element that is essential to life as we know it. We have just explored 12 elements out of more than 100, and we will continue our review of the elements and some of the laws of physics and chemistry that help us understand how they work next time. In the second part, we will resume with element number 13, aluminum, another metal. But for now, we have reached the end of our story for tonight. You can now let go and fall asleep. Or if you are not sleepy yet, you can pick another story from my ever-growing library. And until we meet again, good night. Sleep well.